Students, the PDF PPT is visible. Please, anyone reply me. My voice is audible. Please, anyone reply me. Sir, my voice is audible. Vignesh.
சார் ஆடிபிளா தான் இருக்கு சார்.
Students, anyone reply
ஆடிபிளா
me.
தான் இருக்கு.
Okay, sir. Today we are going to see the topic of fundamental theorem of arithmetic. Fundamental theorem of arithmetic. Okay. So in unit 3, fundamental theorem of arithmetic. So in the first page I shown some figures.
So,
From the
sir, voice audible அல்ல சார், ரொம்ப லோவா இருக்கு.
Okay, பாரு ஒரு 2 seconds பாரு, then you can record. Okay, from the first page I shown one figure. That figure is nothing but in top I have the number 2520. That is, after that I branched into 2, that is 40 into 63. That is 2520 is factored as 40 into 63. Again 40 is factored as 4 into 10. 63 is factored as 7 into 9. Again I can factor 4. Again I can factor 10 as well as 9. This diagram represents what do you mean by fundamental theorem of arithmetic. That is, suppose choose any integer which is greater than or equal to 2 is a prime number or a product of prime numbers. This is nothing but fundamental theorem of arithmetic. Okay. Now my voice is audible. Please anyone reply me.
சார் ரொம்ப லோவா கேக்குது சார்.
லோவா கேக்குதா? ஒரே நிமிஷம். ஓகேமா, கொஞ்சம் சொல்லுங்க, பார்க்குறேன். ஓகே
ஓகே.
Then okay, what do you mean by okay, today date? What is your today date? Anyone? What is your today date? Today date, anyone reply me? Today date is 27/2020. Okay, any special today? In the date of today, any special? Okay, I will show you. The sum is a prime number 13. Just add the sum of 2 plus 0 plus 0 plus 7 plus 2 plus 0 plus 2 plus 0. That is sum is 13, which is a prime number. Okay, next, now continue our study of prime numbers. The first we know that prime numbers is nothing but building blocks of all integers. Okay. In other words, integer greater than or equal to are made up of primes. Okay. By lemma already we know that. That is, every integer greater than or equal to 2 can be decomposed into primes. This result called the fundamental theorem of arithmetic. That is, every integer greater than or equal to 2 can be decomposed into primes. This result called the fundamental theorem of arithmetic, which is certainly the cornerstone of number theory. Okay. Before we start it formally and prove it, we need to lay some groundwork in the form of 2 lemmas. First, lemma 1. If P is a prime and P divides AB, then P divides A or P divides B. What it means that the prime number divides a product of 2 integers, then definitely the prime number divides any one of the integer. Okay. The lemma 2, students, please, I have some disturbance voice, so please mute your mic. Okay, lemma 2, let P be a prime and P divides the product of n integers. Sanjay, mute yourself. Okay, let P be a prime. P divides a product of n integers. then definitely your prime divides at least one of the integers. The lemma says that P is a prime, P divides product of n integers, then definitely P divides one of the integers. Okay, let P be a prime, P divides A1, A2, etc. A, that is a product of n integers, positive integers, then P divides at least some, P divides A for some I is lies between 1 and n. Okay, so the first lemma is prime divides product of two integers, then definitely prime divides any one of the integer. The second lemma, prime divides product of n integers, then definitely prime divides any one of that integer. The corollary. This is important corollary. By using this corollary, we are going to prove the theorem. Okay. In previous two lemmas, A1, A2, AB and A1, A2, AN are integer. But in this corollary, if P all are prime, that is P is a prime, Q1, Q2, etc. Q1 also prime. Okay, then P divides the product of n primes, then definitely P must be equal to any one of the prime, say Qi for some I. That is, there are n plus 1 primes, P is the first prime, the remaining is n primes. P divides the product of n primes, definitely P must be equal to any one of that prime. This is the most important corollary. Next, fundamental theorem of arithmetic. This is an important 8-mark theorem. Okay. Today we are going to see two important 8-mark. One is fundamental theorem of arithmetic. Another one, there are infinitely many primes of the form 4n plus 3. Out of these two 8-mark theorem, definitely one may be asked for the university examination. Okay. What do you mean by fundamental theorem of arithmetic? Every integer n greater than or equal to 2 either is a prime or can be expressed as a product of primes. The factorization into primes is unique except for the order of the factors. That is, first you have to know one thing, that is every integer n greater than or equal to 2 either is a prime or can be expressed as the product of prime. Okay, what do you mean by the next sentence? The factorization into primes is unique except for the order of the factor. That means, suppose you want to factorize uh, 20 or 60. Suppose you want to factorize 60, how do you factorize? That is 5 into 4 into 3. Okay, 20, 20 into 3, 60. So the one representation is 3 into 2 square into 5. This is one representation. The another representation, 2 square into 3 into 5. You may think that this is another representation, but both are same. That is, if you write 3 into 2 square into 5 or 2 square into 3 into 5, both are same representation. It's not a different representation. This is tell that the factorization into prime is unique except for the order of the factors. Okay, proof. First, let us prove that every integer n greater than or equal to 2 either is a prime or can be expressed as the product of prime numbers. First, I am going to prove if you choose any integer which is greater than or equal to either prime or can be expressed as the product of prime numbers. Okay. So the proof is very simple. In first page already shown on figure, that is 2520. So in that figure, what I did, that is written by the letters. That's all. Okay. So what I did, first I choose a number, then factor into two numbers. Again, one of the number is again factor into two numbers. The another number is again factored into two numbers. When we stop, the factor is a product of two primes. We stop the procedure. That is my proof. Okay. Let n greater than or equal to be an integer. N equal to 2 be an integer. First case, n is a prime, then n cannot be factor further. So if it is n is a prime, n cannot be factor. Okay. So in this case, the theorem is proved. N is prime, nothing to be proved here. Okay. So n is not a prime. That is, n can be written as, that is, n is not a prime means n is composite. Definitely composite number means definitely composite number has two factors, say n is a composite number, say I can write, I can n can be written as n equal to n1 into n2. So the values of n1 n2 is greater than 1 and less than n. See, because prime number means the only factors are 1 and itself. Composite means definitely it has more than at least two prime numbers except one. Okay, at least other than one, you have two factors. So only here I can write n equal to n1 into n2, at least n1 into n2. So one is less than n1 comma n2 less than n. Okay, now we can think about n1. If it is n1 is prime, then theorem is holds good. Nothing to be proved. If n is not a prime, that is n is a composite, again I can factorize n1 as n3 into n4. So n3 n4s are greater than 1, less than n1. Okay, similarly we can proceed for n2 n3 n4 n5 and so on until n can be expressed as the product of prime numbers. Okay, so did you understand? First I choose a number, I try to factorize into two integers. Any one of the integers is a prime, the theorem holds good. Suppose that first number is not a prime, again it's behave as a composite. Composite means I can represent as a product of two integer. So one of the integer is prime, the theorem is holds good. Otherwise, again I can factorize into two number and so on. When we stop the procedure, finally we have product of two prime numbers, then I can stop the procedure. Okay. Next, we will prove the uniqueness part. Suppose n greater than or equal to 2 has two representation of prime product of primes. Suppose n greater than or equal to has two representation of product of primes. Say n equal to p1, p2, p3, etc. pr, which is equal to q1, q2, q3, etc. qs. That is n equal to p1, p2, p3, etc. pr. Again n equal to q1, q2, q3, etc. qs. I assume that n has two set of factorization. Okay. By cancelling the common factor, we may assume that PA not equal to QJ. That is, suppose out of the two representation, suppose you have a common factor, you can cancel it. Then finally, I assume that none of the PA is equal to none of the QY. That is, PA is not equal to QJ. Okay, we know that PA is divides P1, P2, etc. PR, because PA is nothing but any one of the prime from P1 to PR. So P definitely divides the product because P1, P2, PR in the product there is a prime PI. So definitely PA divides P1, P2, P3, etc. PR. PA divides the product of R prime, definitely PA divides the product of S prime. Say PA divides Q1, Q2, Q3, etc. QS. Because the both the representation is same, so the PA divides the N prime, definitely PA divides the S primes, that is Q1, Q2, X3, Q3, etc. QS, which implies PI divides QI. So one corollary says that that is P Q1, Q2, Q3, etc. Q1 are prime. P divides the product of n prime. P must be equal to any one of the prime. Already we seen the corollary. By using the corollary, so we say that PI must PA divides any one of the prime means definitely PA divides one of the prime. Here PA divides product of S prime, definitely PA divides one of that prime. Okay, so PA divides QI, which implies by previous lemma PA equal to QI because P, Q1, Q2, etc. Q1 are prime numbers. P divides the product of n prime numbers, definitely PA equal to QJ. One thing you have to understand clearly, a prime cannot divide the another prime. You have to remember one thing very carefully. A prime cannot divide the another prime because prime number has a only factors of 1 in itself. So the prime 3 cannot divide 5. 5 cannot divide 7. So prime itself, prime number only we can divide. That is 3 divides 3, 5 divides 5. So a prime divides a product means definitely the prime is equal to one of that product. Then that is PA equal to QY. Okay. So which is contradiction, because in the fourth line we assume that PA not equal to QJ, but we arrive at PA equal to QJ, which is contradiction. So by cancelling out the common factor, nothing will out be. That is, we after cancelling common factor, there is no two primes are equal. That is, PA not equal to QJ, but we arrive at PA equal to QJ. This is contradiction. So why we get this contradiction? We assume that n has two representation of product of primes. Hence, n has uniquely expressed as the product of prime numbers. Okay. Do you have any doubt in this? Do you have any doubt in this?
No, sir.
Please read out the. So I will send the PPT. That is, I will upload the PPT in your Google Classroom. So please go through it at least 2 to 3 times. Line you have to study. If you have any doubt, please ask me. Okay, because suppose I teach the theorem to one means definitely each and every student can understand the theorem. So when I teach one to many, many of them has the doubt. Okay, study yourself. If you have any doubt, in any line, please ask me. Okay, call me and clear your doubt. Okay. Now we can move on to another next statement. Observation. It follows from the theorem that every composite number n can be factored into primes. From the previous theorem, I can observe that every composite number n can be factored into primes. Such factorization is called prime factorization of n. Such factorization is called prime factorization of m. For example, take number 5544. This can be factorized into 2 into 2 into 3 into 7 into 2 into 11 into 3 is a prime factorization of 5544. Okay. Another observation. Using exponential notation, that is, this product is often written as 5544, which is equal to 2 cube into 3 square into 7 into 11. Such product is a prime power decomposition of m. Such product is the prime power decomposition of n. Okay. If the primes occur in increasing order or ascending order, then it is the canonical decomposition. Okay, because in next topic is canonical decomposition. Canonical decomposition is nothing but it's a prime factorization, but the primes are in the ascending order. That is called canonical decomposition. Okay, now see the definition of canonical decomposition. So the canonical decomposition of a positive integer n is of the form n equal to p1 power a1 into p2 power a2 etc. pk power ak, where p1, p2, pk are distinct primes with p1 less than p2 less than etc. less than pr. That is, each prime are in the ascending order, and each ai exponent ai is a positive integer. Okay. This is the definition of canonical decomposition. Canonical decomposition is nothing but prime factorization. The prime numbers are in the ascending order. That's all. Problem 1. Find the canonical decomposition. Already you know very well. That is, using L division method, we can easily find the canonical decomposition. Okay, that is 2550 as represented as 2 into 2 into 2 into 3 into 3 into 5 into 7. By using L division method, easily you can write it. So canonical decomposition means what I told. You have to write the prime number in ascending order. That is 2 cube into 3 square into 5 into 7. This is canonical decomposition, which is a desired canonical decomposition. This is L division method. There is another method. Find the same problem. I use the another method. So first I can find the product 2520 as product of two integers. First I am able to write a given number is represented as product of uh, two integers. After that, again I can factor a 40 as 4 into 10, 63 as factored into 7 into 9. Again I can factor 4 as 2 into 2, 10 as 2 into 5, 7 as it is 7, 9 as 3 into 3. Now again rearrange it, 2 cube into 3 square into 5 into 7. Okay, which is a desired canonical decomposition. L division method is up to me. L division method is the easiest one. Okay, so so this is suppose the given number is a huge number means by using L division method is take a long duration. So only we use the second method also. Okay. Observation. The above method can be illustrated in a tree diagram, so called a factor T. In such diagram, if A divides B, we connect them by a line segment. Okay. So only I give the message in the first page of our PPD. Okay, 2520 as factor as 40 into 63. 40 is factor as 4 into 10. 4 as factor as 2 into 2. 10 as factor 2 into 5, 63 as factored as 7 into 9, so 9 is factored as 3 into 3. Next, so this is another 2 mark problem, important problem. Find the positive factors of 63. Find the positive factors of 63. Please listen carefully. So first we notice that 60 is equal to 2 square into 3 into 5. By L division method we can easily factorize 60 is 2 square into 3 into 5, but we have to find the positive factors of all positive factors of 60. Okay, so how do you do this? By fundamental theorem of arithmetic, every factor of 60 is of the form 2 power a into 3 power b into 5 power c, because 60 is factored into 2 power 2, 3 power 1, 5 power 1. So every factor of 60 is of the form 2 power a into 3 power b into 5 power c. So A is varying from 0 to 2, B and C are varying from 0 to 1, because 2 power 2 is the power of 2 is 2, so A varying from 0 to 2. The power of 3 is 1, power of 5 is 1, so B and C are varying from 0 to 1. Okay, so I have to collect all such collection. There is nothing but positive factors of all collection of positive factors of 60. Okay, the various factors are this. How do you write this? I will show you. Okay. See, suppose what is the A varying from 0, 1, 2. So A varying from 0, 1, 2, B varying from 0 to 1, C varying from 0 to 1. Now I have to collect all such collections. Okay. So first I fix 0. So first my collection is 0, 0, 0. That is 2 per 0, 3 per 0, then 5 per 0. The next collection 0, 0, 1. Okay. That is 2 factors. Okay. Then 0, the next one 0, 1, 0. 0, 1, 0. Next one 0, 1, 1. Okay. After that the 0 is over. For using 0 I can able to write 4 factor. Now I am going to by using 1 I am going to write 4 factor. That is I can use another color, green. Okay. So 1, 0, 0, 1, 0, 1. So 101 fourth one, 100 fourth one, 101 fifth one, then 110, then 111. I will get the remaining 4. Now I choose another color. So pink. Next one 2. So 201, 20, sorry, 200, 201, 200, 201. Next 210, 211. Finally we will get all such collection, that is for find the positive factors of 60 is nothing but there are 12 factors. There are 12 factors. Count it, you will easily check it. So first write the possible of a value. What are the possible of a value? 0, 1, 2. After the write the possibility of b, 0, 1. Write the possibility of c, 0, 1. Okay. Then so just combination of all three ABC. So you have to choose all such collections combination of ABC. There is nothing but all positive integers of positive factors of 60. Okay. And now you can easily evaluate. The factors are 1, 1, 2, 4, 5, 10, 20, 3, 6, 12, and 15, 30, 60. There are 12 positive factors for the integer 60. Okay. Did you understand? Do you have any doubt? Thus, 60 has 12 factors. Okay, the next another interesting is a sequence of 0 in the decimal representation of a number after which no other digits follows. That is sequence of 0 in the decimal representation of number after which no other digits follows. That means suppose in the value of 100 the trailing zeros are 2. In the value of 1000 the trailing zeros are 3. Suppose 2500 in that value the trailing zeros are 2. Suppose 1 lakh the trailing zeros are 5. Do you understand what I mean by trailing zero? In that value we have a sequence of 0. After that 0 no digit will follow. That is end of the value how many zeros are there, each and every value end of the digit, that is unit place or unit place, 100 place, 1000 place, 10,000 place, and lakh place. So in the place how many zeros are there? So in unit place definitely 10, 100 place definitely 10, 1000 place definitely 10. So how many zeros are there? That is called by trailing zeros. Okay. The number of trailing zeros in the decimal expansion n factorial by using the formula. That is, the formula is nothing but floor function of n divided by 5, floor function of n divided by 5 square plus floor function of n divided by 5 cube plus extra. Use this formula to easily evaluate the trailing zero in the decimal expansion. Okay, sir, how do you get this formula, sir? How do you think that this formula? Okay, it's easy one. In mathematics, each and every formula, each and every problem, we have a proof. Okay. Okay. Next problem I will explain. Okay. Okay. Problem 1. Find the number of trailing zeros in 25. Find the number of trailing zeros in 25 factorial, because we have the formula the trailing zeros of in n factorial. Okay, the formula is floor function of n by 5 plus floor function of n divided by 5 square plus floor function of n divided by 5 cube. Okay. Solution. Okay, I will explain. How do you the formulas exist? Okay, what do you mean by 25 factorial? 1 into 2 into 3 into up to 25. What do you mean by trailing zero? End of the value, how many zeros are you have? Okay, okay. So when we get 0, suppose you want to suppose you do multiplication of two numbers, two integers. When we get 0, anyone please reply me. So product of two integers when we get 0. Which type of in which case the product of two integers, the one of the digit becomes 0. Hello, anyone reply me? Suppose you want to multiply two numbers, the resultant is must contain 0 at the unit place or at the 100 and unit place or at 1000 and 100 and unit place. What are the possibilities? When you multiply two numbers, you will get, at least you will get 0 in the unit place. What is the possible? Okay, no one reply me, I will explain. So if you multiply it by 10, any number multiply by 10, definitely you will get 0 in the unit place. Okay, that means when we get 10, you multiply 2 into 5, you will get 10. So that means I have to search the factors 2 into 5, definitely I will get 1 0. Suppose I want to search the factors 2 into 5, definitely I will get 1 0 because 5 into 10, 2 into 5 become 10, I will get 1 0. Okay, from first to 5 numbers, you can see this. 1 into 2 into 3 into 4 into 5. From this, I can able to find 1 2 as well as 1 5. So from this, I can get 1 0. After this, so I have to search 5 because in factorial function, definitely you will get 2 because even number means from that even number I can get the factor 2. Okay, so I have to search the number 5. That is my ultimate aim. Okay, if you search the number 5, where we get, here I will get 5. Okay, here I will get 5. After that, here I will get 5. After that, here I will get. After that, here I will get 5. After that, here I will get 5. Okay, so definitely I will get 5 5s. From before 5, definitely I will get 1 factor 2. So 2 into 5, 10. Here there is 1 5. So from 8 I can get 1 2. So 5 into 2, 10. Similarly here I will get 5. So in that case, see here I will get 1 5. Similarly 10 I will get 1 5. In 15 I will get 1 5. In 20 I will get 1 5. Okay. So in 25 also I will get 1 5. So there are 5 5s. There are 5 5s. So here I can get 5 into 2, 10. Here also 5 into 2. In 8 I can get factor 2. From 10 I can get factor 5. So 5 into 2, 10. Again from 15 I can get the factor 5. From 14 I can get the factor 2. So again I will get one more 10. From 20 I will get 5. From 18 I can get the factor 2. So again I will get 1 0. From 25 I will get 5. Then from 25 I will get 1 2. So there are 5 zeros. But when you observe 25, see, okay, how do you get this? That is, here the factorial representation only for 25. 25 factorial means I start with 1, end with 25. So how do you search the number which is divisible by 5? There exists a formula, the number of positive integer which is less than or equal to given number and divisible by less than or equal to a and divisible by b. The answer is flow functions of a by b. Already we studied. So here I have to find the number of positive integer which is less than or equal to this 25 as well as divisible by 5. If you search that collection, definitely you will get that much of zeros. So only I use the formula, that is flow functions of n by 5. Okay, sir, how do you get the n by 5 square? See, observe 25. Here I use only 1 5. We have one more 5. How do you collect that 5? That is the other formula, the number of positive integers which is less than or equal to n and divisible by 25. If you add one formula, that again I will get one more 5. I can add the one more 5. So when we add one more formula n by 5 cube, the factorial function is, suppose you want to find the factorial function for 125 or the more than that is 126 factorial or up to the 5 power 4. 5 power 4 is 5 5s are 25, 25 divided by 625. That is from 125 to 624 we can add the third term, that is a flow function of n by 5 cube. Okay. This is the explanation for that one. Okay. Suppose if you understand well and good, otherwise just use the formula. Solution, find the number of trailing zeros in 25 factorial. The solution is, what's the formula? That is n by 5, flow functions of n by 5. plus 4 functions of n by 5 square, because here if you put 4 functions of n by 5 cube, that is 125. Here n is 25, so n by 125 becomes 0 only. So here I have to use only first two terms. So floor functions of 25 by 5 plus floor functions of 25 by 5 square. The answer becomes 5 plus 1 6. So out of 25 factorial, just by using the calculus try to find it. If you find the 25 factorial, definitely it has 6 zeros. At the end of the expression we have 6 zeros. Similarly, we have one more problem, that is find the number of trailing zeros in 234. 234 is greater than 125, so I have to do the formula up to 3 terms. Okay, that is floor function of 234 by 5 plus floor function of 234 by 5 square plus floor functions of 234 by 5 cube. That is 46 plus 9 plus 1, so 56. There are 56 trailing zeros. Okay, the another problem, suppose the highest power of k of a prime number p that divides n factorial. Suppose I'm going to divide a prime, I'm going to divide n factorial by prime. What is the highest power of k? There is a formula. In the previous case, just replace 5 by p, we have a formula. Okay, by using this formula, we can able to do one problem. Find the highest power of 2 that divides 1001 factorial. Find the highest power of 2 that divide the 1001 factorial. So here n is 1001, p is 2. Just apply the formula. Floor function of 1001 by 2 plus 1001 by 2 square up to 1001 by 2 power 29. Okay. So, sir, how do you find this 2 power 29? Just you have to divide 1001 by using simple division. You will get the 29 twos. So, if you bit 2 power 30, it's greater than the 1001. 2 power 30 is greater than the 1001. So, I have to stop 1000 floor functions of 1001 by 2 power 20. The answer is 500 plus 250 plus 125 plus 62 and so on. The answer is 994. Okay, the next problem. Find the value of n for which for what n factorial contains 58 trailing zero. This is a inverse of first problem. That is, we know that. See here, I have to find the answer is 58 trailing zero. For what value of n the n factorial contain 58 trailing zero. Okay. Simply can use 58 equal to n by 5 n cube. You can start with n by up to n by 5 per 4. So you cannot able to find n. Okay. In that case, so you have to restricted the formula up to third terms, 3 terms up to 3. That is n by 5, n by 5 square plus n by 5 cube. Okay. The next lemma. This is important for next theorem. The product of any two integer of the form 4n plus 1 is also the same form. So take two integer of the form 4n plus 1. Say 4n plus 1, 4m plus 1. Just multiply it again, you will get the same form. That is sum 4nm times of 1 something. That is product of two integers of the form 4n plus 1 is also the same form. This lemma I am going to use in your next theorem. Theorem. important 8 mark theorem. The next is important 8 mark theorem. This is the most wanted theorem, so only I give the attention symbol. The statement is nothing but there are infinitely many primes of the form 4n plus 3. The statement is there are infinitely many primes of the form 4n plus 3. Okay, I think it's time. It's time to finish the class. So I will teach the theorem in the next class. Okay. Anybody have doubt? Anybody have any doubt? Okay, the class is up to 9:55. Now I can wind up the class. Okay, thank you, students. Next class we will see the proof of the theorem. There are infinitely many primes of the form 4n plus 3. Okay, thank you.